Today, my thesis partner, Casey Brown, and I will be presenting our senior thesis entitled A Fluid Structure Interaction Analysis of Vertical Lift-Producing Dagger-boards. At this time, I would like to thank our principal advisor, Professor Adrian Onis. The primary objective of our thesis are as follows: to establish a fluid structure interaction method, to evaluate the effects that structural deformation has on the performance of lifting foils, and to understand how to design a more stable foil. A brief outline of our presentation. We begin with a background, move on to some theory, discuss our procedure of our analysis, discuss our results and conclusions, and finally recommend some future work. The 34th America's Cup initiated a large influx of funding into the development of hydrofoil sailing craft. Countless hours of research by the competing teams led to major developments in the vertical lift-producing daggerboards. This major development in daggerboard technology trickled down into mainstream foiling and ultimately resulted in high-aspect CV-type foil dominating. The A-class catamaran, the Knacker 17, the F-18, the Gunboat G4, and the GC-32 catamaran are all examples of this technology, all of which use a CV-type foil, which can be seen here. What is a vertical lift-producing daggerboard? In sailing dynamics, a daggerboard's typical purpose is to resist the side force generated by the sails. In addition to resisting side force, lift-producing daggerboards eliminate displacement and reduce drag, resulting in higher forward speeds. It is common to characterize lifting daggerboards by their frontal profile. Here we can see the foil that we used. You'll see the combination of the C foil with the V tip, also known as the CV foil. The configuration produces both vertical lift and side force, resulting in a bending moment, which can be seen here. This is the primary focus of our thesis. Very little work has been published regarding the performance of CV foils, as America's Cup teams wish to keep their research proprietary in order to remain competitive. There have been a few recent WEBB theses completed. Schatt and Zangri's computational fluid dynamic analysis of curved daggerboards on higher performance sailing yachts compared C, JL, and CV foil configurations, and concluded, similar to America's Cup designs, that the CV foil was optimal. The FAST thesis examined the effects of varying the foil lead angle on the lift and drag characteristics. Both of these theses ignored the effects of deformation in their analysis. Why FSI? We want to include these effects of deformation in our analysis. In the real world, structural deformation deflects foils from the hydrodynamic loading. These deflections typically impact performance on these foils, and our analysis captures these effects. We will break apart our discussion of theory into computational fluid dynamics, finite element analysis, and fluid structure interaction. CFD is a numerical simulation of fluid flows. It decomposes the problem into millions of simple cells, using numerical methods to solve for the flow through all the cells. And the solution includes the flow characteristics of the entire domain. The Navier-Stokes equations are the governing equations behind this type of CFD. They can all be derived from the conservation of mass, conservation of momentum, and the conservation of energy shown on the right. The numerical solution of these equations can describe the motion of viscous fluid flows. A direct solution of the Navier-Stokes equations is not practical. We therefore use a time-averaged version to find the solution. The figure shown on the left decomposes the total velocity into a mean, shown on the left as a red line, and the fluctuating velocity as the blue line. Shown below is the average momentum and continuity equations used by the CFD solver. The equation is shown in tensor notation for the clarity of the gradient terms used in the model, and for the decomposition of shear stress and Reynolds stress. Within the equation, we can see the pressure gradient, viscous normal, and shear stress terms, and the Reynolds stress terms. Depending on the type of solution desired, different terms are utilized. Potential flow only uses the first, laminar flow uses the first two, and turbulent flow uses all of the terms. Moving on to FEA. FEA is a numerical simulation of solid mechanics. It decomposes the problem into millions of simple elements and uses numerical methods to solve the stiffness matrix. The solution includes the stress, strain, and displacement of a solid body. Now, fluid structure interaction is the analysis of the transfer of momentum and forces between a fluid region and a solid body. This method couples FEA and CFD. There are several different methods of FSI. Bodies can be rigid or deformable. It can be a one-way or two-way interaction. There can be both strong or loose coupling, and a dynamic and static simulation can take place. Here we have a flowchart showing a two-way coupling fluid structure interaction algorithm. We begin with initialization, move on to a CFD iteration, which produces pressure gradients, which can be applied to the FE mesh, which then an FEA iteration occurs. The FEA iteration results in a solid displacement. This solid displacement is transferred to the CFD mesh, where the mesh is morphed. Then the simulation is checked for convergence. If there isn't convergence, another iteration occurs until convergence does occur, where we can then proceed to post-processing. For our particular case, we are using a deformable structure because deflections are significant. We are doing a static simulation since the system is in equilibrium, and we are ignoring initial terms. We are doing a two-way coupling, so the effects of structural displacement on the fluid are considered, and we are using a strong coupling since we are looking at an incompressible fluid on a lightweight, flexible structure. Moving on to our procedure. We will go over STAR CCM Plus and our workflow within STAR. We will discuss our testing conditions, discuss a CPU study we did, and discuss our validation procedure. We initially considered many other platforms, but we ultimately chose STAR CCM because of its versatility as a simulation platform and the customer support offered along with it. STAR CCM is a multidisciplinary simulation program. It solves problems involving flow, heat transfer, and stress simultaneously. For us, this allows us to run both the fluid and solid solver in the same environment. CD Adapco also releases a new version of STAR CCM every 4 months, providing enhancements and new features. Of particular interest to us, the January release included a fluid structure interaction coupling model. Moving on to the CFD workflow. We begin with the geometry of the problem. Move on to the meshing pipeline. Physics and boundary conditions are applied. The solver is run, and then the solution is post-processed. The geometry forms a link between computer-aided design and computer-aided engineering. Here we have to decide on an overall solution accuracy required. How detailed do we want to get? Once the CAD file is imported, it is important to check the initial quality of the mesh. If it is not sufficient, the mesh can be repaired in STAR CCM. Shown on the right is our imported IGES mesh. Meshing is the process of discretizing the problem. First, a surface mesh is generated from the imported CAD. Then a control volume is subdivided with finite cells to create a volume mesh around this surface. Then, localized refinements are applied to capture complex flow effects. Now, the solution is very sensitive to the mesh quality, and it is important to have the cells small enough to capture complex flow effects where they need to be. However, it is important to keep the total number of cells down in order to keep the problem computationally economical. Here we have an example of a surface curvature refinement. The leading edge of our foil has a high level of curvature, so we need a large number of cells to accurately refine it. Here's an example of a prism layer in our mesh. The prism layer helps to accurately resolve the boundary layer effects. And here we have an example of a wake refinement region, which helps to resolve turbulence effects downstream of our foil. Additionally, we have a volumetric refinement between the foil and the free surface to capture ventilation and other complex flow effects. We also have a global free surface refinement to resolve the free surface. You'll notice the mesh is distorted here. This is from the mesh morpher. This is a result of the solid displacements being transferred to the CFD mesh and the CFD mesh reacting to the solid displacement. I'd like to bring up Casey Brown now to discuss our physics.
Once you have completed the meshing pipeline, you must select the proper physics models for the simulation. These include gravity and the Reynolds averaged Navier-Stokes equations, as seen earlier in the presentation. Particular importance in our model is turbulence modeling, especially in the boundary layer close to the foil. We chose the K-epsilon model as a compromise between robustness and computational cost. It's a two-layer model that can solve for both the viscous sublayer closest to the wall and the fully turbulent flow further out from the wall. It cannot solve the buffer layer between the two layers. To account for this, you use the y+, which is a non-dimensionalized value representing the distance from the wall relative to the flow velocity. To properly size the thickness of the first mesh layer for the K-epsilon model to function. After that, you must apply the boundary conditions to the simulation. A velocity inlet is assigned to the four sides and front face, not shown. A velocity outlet is assigned to the back face, shown in pink. The foil is modeled as a no-slip wall to account for the viscous and shear forces. At this point, you could run the solver and begin post-processing the results. You can then display different scenes such as pressure, velocity, free surface elevation, shear forces, and cavitation. On the right-hand side here, you can see the free surface elevation with red being high points in the flow and blue being low points. The finite element workflow is fairly similar to the CFD workflow with a few key differences. FEA uses finite elements, which are single points in the mesh, instead of finite volume cells. FEA applies a stiffness matrix instead of a RAND solver to the physics. Boundary conditions include fixed constraints and applied pressure and shear loads. FEA is a second-order solution instead of numerous iterations required for CFD convergence, so it's much shorter computational time. At this point, you can combine the CFD and the FE to create the FSI workflow. You apply the proper meshes to each beginning with the same geometry. Then you apply the proper physics and boundary conditions, and you interface the two simulations to produce your FSI model. At which point you can run the solver and post-process in the same manner you would otherwise. We tested for both the undeformed case, which is CFD only, with the CFD mesh containing 6 million cells, and for the deformed case, where we first converged on a CFD solution, then coupled with the FE model with the FE CFD solution, and ran two-way coupling until that converged. The FE mesh is 1 million cells in addition to the 6 million cells of the CFD mesh. Used aluminum for a material with the Young's modulus of 68 gigapascals. Most of these foils are actually built with carbon fiber, taking advantage of its orthotropic properties. However, Star CCM Plus did not have the capacity to handle the composites at this point, so we chose aluminum as a reasonable simplification. Speeds are tested from 15 to 45 knots with an angle of attack or leeway angle of -1 to 3 degrees for both undeformed and deformed cases. Here you can see that the angle of attack is varied along with the speed of the oncoming flow. We looked for lift along the z-axis, side force along the y-axis, and drag along the x-axis, as these are the key forces that a sailing yacht designer would consider in coming up with a foil design. Before beginning testing matrix, we computed a CPU study which varied the number of cores along the x-axis, along with the runtime shown along the y-axis. We tested this just with the CFD solution with 500 iterations and found that 10 cores was the optimal CPU power for a runtime of 2 hours. We used the same 10 cores for the FSI study, which has a 6-hour solve time with 1,000 iterations. Computational resources that were available to us in the Couch Lab include an Intel Xeon 2.6 GHz processor with 220 gigabytes of RAM. the simulation has been run, you perform a convergence study. As you can see here, there is initial high variance in the solution as the flow is establishing. The CFD then converges and the model is coupled to the FE model at 500 iterations to create the FSI model, which is run for an additional 500 iterations to convergence. The section we used was provided to us by Morelli and Melvin Design and Engineering, and is a generic section used for the AC-50 that will be sailing in the 2017 America's Cup. It is designed for a high lift, low drag ratio. This may result in low stall angles, but for the intended operation conditions, this is very acceptable. Model testing for this type of foil evaluation is almost impossible due to the large Reynolds numbers, especially with the equipment available here. In the real world, America's Cup yacht designers rely on full-scale experiments almost primarily for validation. So we compared to 2D foil theory for a form of validation. Analyzing sections in the foil program XFLR5, which assumes infinite span, we compared that to the non-dimensionalized output forces from the CFD solution, which includes additional complex 3D flow effects, checking for relative similarity. For the FE validation, we took a simple cantilever beam that was fixed at the base with a shear load at the tip with the foil section that we used and compared the theoretical deflection to the finite element model and refined the mesh for the FE model to approach the theoretical solution, at which point we applied the mesh settings to the actual foil model. So in blue here, shown with an angle of attack varying along the x-axis and lift coefficient along the y-axis, you can see the results from XFLR5 for a wider range of angles of attack being tested for than for the CFD shown in red. This is because of the reduced computational time of 2D panel code and the fact that the target operating range is from -1 to 3 degrees. You can see the lift coefficients from the CFD is significantly lower than the 2D lift coefficient. This is due to the 3D effects such as span-wise flow. The lift equation is a function of coefficient of lift, density, velocity, and area. Side force and vertical lift are based off the projected area in those planes. These projected areas change with the formed foil shape. In the red, you can see how the side force projected area decreases, while the lift projected area increases. To follow that up with some results, you can see the variation in angle of attack along the x-axis, with the force in kilonewtons along the y-axis. At 15 knots, there is little variation between the deformed and undeformed cases because of the low pressures encountered. As the speed increases from 30 to 45 knots, there are significant changes compared to the lift performance from the undeformed to deformed cases. This correlates with the expected increase in projected area in the XY plane, leading to an increase in vertical lift. As the side force projected area decreases with deformation, the force generated also decreases. Drag is shown also with an angle of attack along the x-axis and force in kilonewtons along the y-axis. The drag increases with the deformed foil shape. Here you can see the non-dimensionalized lift to drag characteristics of the foil varying angle of attack from -1 to 3 degrees. The 15-knot solution, as evident from previous slides, varies little. However, for both the 30 and 45 knots degrees, Here you can see the non-dimensionalized lift to drag characteristics of the foil varying angle of attack from -1 to 3 degrees. The 15 knot solution, as evident from previous slides, varies little from deformed to undeformed. However, for both 30 to 45 knots, above 2 degrees angle of attack, there is a significant decrease in performance for the deformed foil relative to the undeformed foil. These images show the wall shear stress at 45 knots for -1 degree on the left and 3 degrees on the right. Shear stress is important in this simulation because it is a slender body and friction is the highest component of resistance, a direct function of wall shear stress. You can see at the higher angle of attacks, the increased shear stress resulting in more drag. Here is a visualization of the pressure also at 45 knots at -1 and 3 degrees. You can see the increased flow pressure region on the inside of the foil as the angle of attack increases. Here we are visualizing the saturation pressure. These bubbles are where the pressure drops below saturation pressure, and it is possible for cavitation to occur in these regions. Our analysis did not take into account the physics of cavitation, but future work may want to incorporate this as it can alter the simulation results. Here's a stress visualization. You can see a stress concentration just below the end of the dagger-board chunk, where the fixed constraints are as expected. Some conclusions. We established a powerful procedure for fluid structure interaction analysis in STAR CCM+. The undeformed results show increases in drag, lift, and side force at higher speeds and operating angles as expected. Deformed results show a decrease in side force along with a decrease in projected area, along with an increase in lift and drag with an increase in the projected area for lift. Few recommendations for future work. You could couple STAR CCM Plus with composite FEA software to get a more realistic foil deformation. You could develop a physics cavitation model in STAR CCM Plus to refine those areas below the saturation pressure. You could investigate unsteady flow effects such as flutter in the foil. You could use the developed FSI procedure to optimize the foil design. Now I'd like to invite Dylan and Mike up to present their thesis and hold any questions.
So the feature for the STAR program that you guys were using came out in January. Was that January of this year? If so, how did that affect your thesis timeline?
So you could, I mean, we were already working on the fluid structure coupling. Before the model came out, you could still do the exact same thing. It was just a little bit more difficult. It just tied together a lot of the features in one module, really. It did, it did help make things easier.
Did your analysis include torsional deflection or just in the worship direction?
It's all included. Yeah, just fix up the constraints. That's it.
So for Cody and Casey, I was a bit confused. Did you change your projected area based on the deformed case, or did you use the unformed throughout?
The projected area varies,
For the non-dimensionalization, we used one area, and we're just really developing.
Okay, that's all I want to know.
Yeah.
If you change the area to the unformed, you have to know the unformed in order for the coefficient to be.
Yeah, that needs to be
we
different.
basically use the expanded area in the combined total.
Anybody else?
Yeah, for a trading case, why did you use aluminum as a substitute for composites?
FA in composites is very complex, and especially putting that into a CFD solver is also complex. Aluminum is
As far as our choice in metals,
it's actually default STAR. Yeah, probably the closest we can get. I mean, they make foils out of aluminum prototypes.
Okay.
Did you consider the movement of the foil in Z axis?
No, it's fixed. So that would be the dynamic fluid body interaction. So that'd be another important we have to decide. Which we didn't do. We keep going. It's more complicated.